everyone. I'm CS Hong from Kyung University. Today, I'll be talking about how federated learning is empowering, enhanced, or advanced collaborative intelligence. Here is the outline I'll be following today. First, I will talk about the current limitations of federated learning. And next, I will go over 4 approaches that can help overcome these limitations. After that, I will explain how these approaches can be integrated into our federated learning system. Then finally, I'll wrap up the presentation with some conclusions. Let me talk about the key limitations of federated learning. First, traditional federated learning system operate in server-driven manner without interaction between client. While client process their local data and send update to the server, there is no collaboration or coordination between client. When learning objective change, the new data is introduced or data distribution shift, federated learning system often require retraining because they cannot dynamically adjust. Third, traditional FL applies the same learning strategy across all clients, ignoring the differences in data distribution, which reduces overall efficiency. Lastly, limited computational and communication resources slow down model update and impact system performance. Dealing with these challenges is absolutely crucial if we want federated learning systems to be truly effective in real-world applications. Our goal is to transform FL into unadaptive and collaborative system that can dynamically respond to changes in objectives and environment. We introduce techniques that can be integrated into federated learning for adaptability, proactive environmental adjust, robust learning in diverse data distributions and efficient resource utilization. For example, to tackle suboptimality and enhance the collaboration, we have introduced MP-FedCL. For adaptability, we have developed FRED and RLAIF, that's the AI feedback. And to boost the resource efficiency, we are using HMDC. These techniques are designed to address the challenges in different harsh learning environment. That I will briefly introduce each and explain how they can be integrated into federated learning. Okay, now let's discuss MP-FedCL approach, which stands for Multiprototype, federated contrastive learning. Traditional federated learning uses a single prototype, right? That single prototype that here. This is for each class, but this approach is sufficient to handle real-world data diversity. If you represent the puppy class with a single average value, it won't be able to tell the difference between white puppies and black puppies. Here is a prototype or the representative central point, right? This that represent a class, just for representing a class. To solve this problem, we developed a multi-prototype. Okay, multi-prototype in the Federated Learning to adapt to diverse and complex data distribution across client. This approach is robust to non-IID data because multi-prototype can represent class diversity. Okay, let's take a closer look at the overall architecture and the procedures of the MP-FedCL framework. MP-FedCL framework is designed to balance local training and global aggregation, specifically to address non-IID data challenges. Here is how it works. First, each client trains locally using its own data, optimizing or supervised loads and contrastive loads to improve class separation. After training, clients send their gradient and local prototypes to the server. The server then aggregate this update to refine the global model and build a global prototype pool, which captures the diversity of data across all clients. This updated model and prototypes are sent back to a client and process continue in cycles. At inference time, the global prototype pool is used for classification, ensuring that MP-FedCL delivers strong performance by effectively adapting to diverse and non-IID data. Now let me share the result. The MP-FedCL showed in better accuracy and the more robust performance compared to the baseline method. Okay, we tested it under two scenarios. The first is the future non-IID setting, where all clients share same class labels, but have different future distributions. Second is that is label on an IID setting where clients have imbalanced or non-overlapping class distributions. In the future non-IID setting, MP-FedCL achieved the highest top 1 average test accuracy on the digit 5 dataset, outperforming all the baseline method. In the label, the non-IID setting, MP-FedCL again delivered superior top 1 average test accuracy across various databases compared to their baselines. Lastly, when we evaluated the average test accuracy under these non-IID conditions, MP-FedCL consistently performed better on digit 5 and Office 10 proving its robust and adaptability. Okay. Now let me introduce PRED, which stands for Pre-emptive Action Revision by Environmental Feedback. There are three main problems with current embodied AI. It makes the mistakes or takes wrong actions when environment does not match expectations. It only correct the plans after a task fails, which can lead to irreversible irreversible consequences. It wastes time and resources by taking unnecessary actions or interacting with wrong object, slowing down the task executions. To tackle these challenges, PRED introduced 4 key approaches. Okay, we have some these 4 key approaches here. That first, APM, or that attribute plan modification, update plans in real time by checking object attribute, allowing it to skip unnecessary actions. The second, DTA, dynamic target adaptation, adjust the target dynamically when an object actual location does not match its expected location. Okay. Third, OHV object heterogeneity verification, that it makes the sure object match expectations, preventing mistakes. And then finally, ASR action skipping by relationship, analyze object relationships to avoid redundant actions. These 4 approaches work together to make tasks more efficient and accurate. This slide explains the detailed step of PRED. Okay, it shows us some kind of scenario. You can see that figure of that scenario. First, the large language model create an initial action sequence based on the natural language instructions. Next, it compares the expected environmental state with the actual observed state to identify any discrepancies. Then these discrepancies are recorded and turned into a feedback prompt. The feedback prompt is fed back into large language model, which generate a revised sequence here. Okay. These steps help AI agent dynamically adapt their actions and reduce errors, improve task efficiency in real-world environment. Okay, let's go over the experimental result for PRED and how it compares to the SOTA method. On the teach benchmark here, okay, that this PRED achieves highest success rate SR and goal condition success rate GC in both seen and unseen environment. This shows that its robustness in handling dynamic and complex task scenarios. Specifically, on the task-focused dataset TFD, PRED performs the baseline method by dynamically adapting plans to situational changes. The high pass ranks weighted PLW scores also demonstrate PRED's the efficiency, reducing unnecessary action and completing tasks more effectively. Now, looking at Alfred framework here, right? This one that that this one is the PRED. PRED delivers superior performance in both seen and unseen environment. Once again, achieving the highest SR and GC. This result highlight PRED ability to handle a wide range of environments while maintaining accuracy and efficiency. Let me introduce RLAIF. this AI feedback, which stands for that is this RL from AI feedback. This approach tackles the challenge of low-quality video text dataset, which often prevent method from the effectively the understanding the association between video that contents and text. In the future, you can see the on example of the multimodal instruction where a video is paired with the question like, can you describe event taking place in the video? Existing models like SFT supervised fine-tuning that that often that fail to align the video and text properly. For instance, the output as shown in the this output B here. Okay, there's output B here. That you can understand that it has the RAX temporal and visual the alignment with the video input. The key idea of RLAIF is to use the AI feedback to better align video and text through reinforcement learning. That using this approach, we train the multimodal SFT model, which we call VRM, RLAIF, to achieve much better alignment between video and text. This slide explains how the reward model is learned in RLAIF. RLAIF works in three main steps. First, we have these three steps here. That it generates response using the multimodal SFT model with high temperature the parameters like 0.7. This created diverse responses from the same input. Next, we collect the context-aware. This here, the preferences in this step model compares the two responses and select the better one. AI feedback is used here to determine which response align more accurately with the video. Finally, that reward, this reward, the model is trained to assign scores to the responses based on preferences collected in the previous step. These three steps and the method enable RLAIF to refine its understanding and improve alignment that between video and text. Okay. Now let me share the experimental result of this proposed model. First, on the left-hand side, here, left-hand side, we analyze the effect of the context information on video-based generative performance. Using context information during preference selection significantly improved performance as shown in the second and third row here. Additionally, segmentation of video into multiple clips and arranging their captions as context boosted the performance even further in the third and fourth here. Okay, the rows. Next, on the right hand here, that we evaluated the training procedure for Pre-emptive SFT. The first and second row highlights how incorporating on additional data set helps improve performance. Finally, the curriculum learning had a substantial impact. Here we include this curriculum learning. if you use this that shown in that last row, further the enhancing the overall result. Okay. On the left-hand side, that later chart that compares the performance of the VRM SFT in the pink color and VRM RLAIF in green color that across metrics such as the correctness, consistency, and temporal alignment and context. And VRM RLAIF consistently outperform the VRM SFT across all benchmarks, demonstrating better alignment with video contents and greater accuracy in generating responses. On the right-hand side, okay, we have examples comparing the responses generated by the VRM SFT and VRM RLAIF. As you can see that the RLAIF clearly performs the SFT. Here the blue text here, blue text, and this one highlights accurate video-based responses, while the red text show that less precise ones. This demonstrates how the RLAIF improves the alignment between the video and text. Okay. Now let me introduce the HMDC, which stands for heterogeneous model dataset condensation. The traditional dataset condensation method often use this single model like CNN or VIT to create a synthetic data set. This can cause the condensed data set to overfit to the specific model, limiting their generalization to other models. HMDC solve this by using multiple models like CNN and VIT to ensure the diversity. It aligns the gradient of the synthetic dataset with those of the original dataset, maintaining fidelity while avoiding bias toward any single model. Gradient balancing ensure actually that the gradient from the both models are balanced, so synthetic dataset performs consistently across all models. The process separates spatial and semantic features through mutual distillation between the models here. Okay. The process separate that what I said, that is that's the mutual distillation and two models. Finally, synthetic dataset is gradually optimized for gradient and future alignment. Now let's take a look at the experimental result of HMDC and how it performs across different model architectures. This table at the top compares HMDC's performance with other methods like random and dream on Cypher10 across various models, including the convolutional net and ResNet and VIT. While most models experience significant performance drops when their architecture changes, HMDC consistently maintains strong performance across all architectures. Additionally, HMDC achieves highest average performance across models, significantly outperforming random the baselines. This result highlights HMDC ability to generalize effectively to different model types. Okay. Now let's talk about how these approaches can be integrated into federated learning. The framework includes 4 key approaches to enhance collaborative intelligence in FL. First, MP-FedCL is applied at the client level to handle non-IID data effectively. Next, HMDC is this one support data set generation for diverse models, improving generalization across client. Then FRED and AIF is integrated at the Federated Learning server level to enhance decision making and model alignment through real-time feedback mechanism. Together, these approaches boost data efficiency, adaptability, automacy, and collaboration within the federated learning environment. Okay. Let me conclude the presentation. In this presentation, we look at how the MP-FedCL, AIF, FRED, and HMDC tackle the major challenges in federated learning. Actually, this presentation has the 4 papers that our team had published. Okay. Okay, so that we are going to define the system requirement and systematically integrate this technology into real-world federated learning development. Actually, to have this proposal can have the practical impact in the future. Thank you.
Thank you, Professor Choong Seon for your talk. So, any questions? Okay, one question.
Thank you for your great talk. I would like to ask how the clients can collaborate in the proposed framework and what kind of feedback can be provided to the Federated Learning server in your proposed framework.
Okay. That as I mentioned, that is federated learning is just having that the cumulative then weight average generally in this federated learning server. As I mentioned in that my conclusion talk, that is, we hope that if we adopt the AI feedback that dynamically from the client side, I believe that is we can provide more accurate the global model to client. Okay. Thank you.
Thank you, Professor.